In this video, we're going to learn about two very important functions, the unit step function and the Dirac delta function, along with the second shifting theorem. Now, you might be wondering, why do we even need these? Here's the big picture. When we're solving a second-order differential equation like this one, the right-hand side, f of t, is called the forcing function or the input. In many real-world applications, that input is not a nice smooth function. It is discontinuous. It turns on or off or delivers a sudden jolt. Think about a light switch. Before you turn it on, the voltage is 0. And then the instant you turn it on, it jumps to 120 volts and then stays there. For a spring system driven by this kind of input, we might write something like y double prime plus y is equal to 120 times u of t minus 1. U of t minus 1 is called the unit step function. It turns on at t is equal to 1, and then it stays on. Now think about a hammer striking a spring. The hammer contacts the system for an instant, delivering a huge impulse. That's exactly what the Dirac delta function models. For that system, written as y double prime plus y is equal to delta of t minus 1, the delta function acts only at the single instant when t is equal to 1. Both of these differential equations can be solved using Laplace transforms once we understand these functions and also understand the second shifting or translation theorem. Let's first learn about the unit step function, otherwise known as the Heaviside function. This function is written as u sub a of t or u of t minus a, and it's equal to 0 when t is greater than or equal to 0 or less than a, and it's equal to 1 when t is greater than or equal to a. Its graph is exactly what you would expect. It's 0 to the left of a, and then it jumps at t is equal to a to 1, and then stays there. It's simple, but incredibly useful. The Laplace transform of this function is equal to e to the minus as all divided by s. Notice what happens here. A shift in time, that delay of a, introduces an exponential factor e to the minus as in the Laplace transform. Keep that in mind because that is the heart of the second shifting theorem. We can also use the unit step function to turn on any function f of t at t is equal to a. The graph of f of t times u of t minus a is 0 before t equals a, and then f of t switches on at that point. To find the Laplace transform of this function, we'll need what's called the second shifting or translation theorem. We'll talk about that after we work through a couple of examples. We're going to work through two examples step by step where we're going to write a function using a unit step function, and then we'll find its Laplace transform. In our first example, f of t is equal to 0 when t is greater than or equal to 0 but less than 3, and then it's equal to 2 when t is greater than or equal to 3. Let's graph this so that we can visualize what it looks like. We'll let this be f and this be t, and then we'll let this point here be 3. Our function is 0 between 0 and 3, and then at 3 it jumps to a value of 2 and remains at that value. We can write this using a unit step function as f of t is equal to 2 times u of t minus 3. This just means that our function is 2 when t is greater than or equal to 3. Now let's find the Laplace transform. The Laplace transform of our function f of t is equal to the Laplace transform of 2 times u of t minus 3. We can bring the 2 out in front, and we just have the Laplace transform of u of t minus 3. The formula for the Laplace transform of u of t minus a is equal to e to the minus as all divided by s. In our problem, a is equal to 3. This gives us an answer of 2, and then we have e to the minus as, a is 3, so we have e to the minus 3s, and all of this gets divided by s. And there's our answer. Let's look at our second example. I wanted to do one like this because it's just the opposite of what we just did. In this example, our function f of t is equal to 2 at the beginning, and then when t is equal to 3, it becomes 0. Let's go ahead and let's graph this. We have f, we have t, we'll put the point 3 right here, and we'll put this point as 2. Our function starts at 0, and then goes all the way to 3, and we'll put an open circle here, and then at 3, it becomes 0. Here, our function is first on, and then it turns off. We can write this as f of t is equal to 2. That's what it starts out with. And then it becomes 0. So what we have to do is we have to subtract off 2 times u of t minus 3. And that way, it's going to go to 0. Let's now find the Laplace transform of this function. This is the Laplace transform of 2, and we'll go ahead and pull out this next 2. So we have minus 2, the Laplace transform of u of t minus 3. The Laplace transform of a constant is that constant times 1 over s, so this gives us 2 over s, and then we have minus 2, and the Laplace transform of our unit step function, when a is equal to 3, is going to be e to the minus 3s divided by s. We can write this as 2, we'll bring that out in front, and then we have a 1 minus e to the minus 3s, and all of this is divided by s. And there's our transform. Let's now learn about the second shifting or translation theorem. We need this theorem to find the Laplace transform of a function that isn't a constant and turns on at a specific point in time. Let's look at an example. We want to express f of t using a unit step function and then find its Laplace transform. Our function f of t is equal to t when t is greater than or equal to 0 but less than 3, and then at 3, it's equal to 0. Let's graph our function. We'll put f here, and we'll put t here, and we'll let this point be equal to 3. Our function is going to be equal to t between 0 and 3. So we'll put an open circle here at 3, we'll put a closed circle at 0, and a line in between. And then at 3, we'll put a closed circle, and it's equal to 0. Let's now write f of t using a unit step function. We'll start with f of t, and notice that it starts with t, so we'll say that it is equal to t, and then we have to turn this t off at t is equal to 3. So we're going to subtract t times u of t minus 3. Let's now find the Laplace transform. The Laplace transform of f of t is the Laplace transform of t minus the Laplace transform of t times u of t minus 3. The Laplace transform of t is equal to 1 over s squared, and then we need to find the Laplace transform of t times u of t minus 3. We actually don't know what this is. We know the Laplace transform of just u of t minus a, but we don't know the Laplace transform of a function times u of t minus a. The second shifting theorem is going to tell us what this transform is. Before we talk about the second shifting theorem, you might be wondering, well, what is the first shifting theorem? The first shifting theorem tells us that the Laplace transform of e to the at times f of t is just f of s minus a. The exponential shifts the transform in the s domain, and s becomes s minus a. The second shifting theorem tells us that the Laplace transform of f of t minus a times u of t minus a is equal to e to the minus as times f of s. This delay in time, represented by this a and this a, becomes a factor of e to the minus as, that's right here, in the s domain. The key to using this theorem is to be able to take your function f of t and change it to a function of t minus a. We're going to do that right now. Let's go back up here to our example. What we need to do now is evaluate this Laplace transform, and we can do that with the second shifting theorem. We had the Laplace transform of f of t was equal to the Laplace transform of t minus the Laplace transform of t times u of t minus 3. We already saw that the Laplace transform of t is 1 over s squared. Now we're going to use the second shifting theorem to evaluate this Laplace transform. What we're going to do is we're going to replace t with t minus 3. So we're going to say that t is equal to t minus 3, and we can't change it, so we have to then add 3. That way, we have our t minus 3, and then we have a constant, and we know how to work with both of those. So this becomes minus the Laplace transform of t minus 3 times u of t minus 3. I'm splitting it up, plus 3 times u of t minus 3. Now this is equal to 1 over s squared minus the Laplace transform of t minus 3 times u of t minus 3. So this is just e to the minus as, which is 3s, times f of s, which is the Laplace transform of t. And then, making sure to carry our negative through, we have minus 3 times the Laplace transform of our unit step function, and that is e to the minus 3s divided by s. This gives us 1 over s squared minus e to the minus 3s divided by s squared minus our 3e to the minus 3s divided by s. Let's combine our s squared terms, and we have 1 minus e to the minus 3s, all divided by s squared, and then we have minus 3e to the minus 3s divided by s. And there's our Laplace transform. We're going to use Laplace transforms to solve an ordinary differential equation where the forcing function, or input, is a unit step function. The equation that we're going to be solving is y double prime plus y is equal to 120 times u of t minus 1. The forcing function is equal to 0, and then it turns on when t is equal to 1. Let's start by taking the Laplace transform of every term in our equation. We have the Laplace transform of y double prime plus the Laplace transform of y is equal to the Laplace transform of 120 times u of t minus 1. Over here on the right, I've written down the formulas for the Laplace transforms of derivatives. We have y double prime, so this is s squared capital Y of s minus s little y of 0 minus little y prime of 0. Those are our initial conditions. And then we have plus capital Y of s. And then on the right, we can pull out the 120 and the Laplace transform of a unit step function. Let's go up here to the top. The Laplace transform of a unit step function t minus a is equal to e to the minus as over s. And our function a is equal to 1, so this is e to the minus s divided by s. Our initial conditions are equal to 0, so these terms are going to go to 0, and we can combine our capital Y of s, so we get s squared plus 1 capital Y of s is equal to 120 e to the minus s all divided by s. Let's get capital Y of s by itself, and this gives us 120 e to the minus s all divided by s times s squared plus 1. Our solution, y of t, is the inverse Laplace transform of capital Y of s. So we need to find the inverse Laplace transform of this function. Let's think of y of s as 120 e to the minus s capital F of s. Let's first find the inverse Laplace transform of capital F of s. Using partial fractions, we're going to write f of s as 1 all divided by s times s squared plus 1. We'll split this up as a divided by s plus bs plus c. That's because we have a quadratic in the denominator, and our denominator is s squared plus 1. Let's go ahead and let's recombine this. So we have a times s squared plus 1 plus bs plus c times s all divided by s times s squared plus 1. Now we can go ahead and set 1 equal to this algebraic expression. To make things easier, I'm going to write the 1 as 0 times s squared plus 0 times s plus 1. And let's go ahead and let's multiply out the right-hand side. This is as squared plus a plus bs squared plus c times s. Our 0 is then a plus b. Our 0 times s is c times s, so we can say that 0 is equal to c, and then we have our constants, and we have a 1 equal to a. That's nice. So we know that 1 is equal to a, so that tells us up here that b is minus 1. This gives us our capital F of s is equal to 1 over s minus s all over s squared plus 1. Let's now rewrite our capital Y of s as 120 times e to the minus s times our f of s, which we just found to be 1 over s minus s all over s squared plus 1. Now we can find the inverse Laplace transform. I went ahead and wrote down the formula over here on the right. if we have e to the minus as times capital F of s, the inverse Laplace transform of this is f of t minus a times u of t minus a. Let's write down that a is equal to 1, and this is our capital F of s. So the first thing we need to do is find little f of t, and then we can shift it. The inverse Laplace transform of capital F of s is the inverse Laplace transform of 1 over s minus s over s squared plus 1. We know what both of these terms are. The inverse Laplace transform of 1 over s is just 1. And then the inverse Laplace transform of s over s squared plus 1 is cosine. So we have minus cosine t. So little f of t is 1 minus cosine t. Now let's find our answer. Little y of t is going to be the inverse Laplace transform. We'll bring our 120 down. And then we're going to have this piece right here looking over in this box, f of t minus a. So that is 1 minus cosine. A is 1, so we have cosine t minus 1. And we're going to multiply that by u of t minus a, which is t minus 1. And there's the solution to our differential equation. Notice that the solution starts at 0 because of this term right here, and then it turns on at t is equal to 1 and oscillates indefinitely. We're now going to learn about the Dirac delta function and walk step by step through solving a differential equation that has a Dirac delta function as its input or forcing function. The Dirac delta function, written as delta of t minus a, represents an instantaneous input at t is equal to a. Think of it as a hammer strike, a huge force delivered for an infinitely short instant. Here's the formal definition. Delta of t minus a is 0 everywhere except at t is equal to a, where it represents an infinitely tall spike with an area of exactly 1. Unlike the unit step function, which stays on, the delta function acts only at a single instant, and then it's gone. Here's how we notate that it represents an infinitely tall spike with an area of 1. The delta function also has this remarkable shifting property. It picks out the value of a function at exactly t is equal to a. Using this shifting property, the Laplace transform of the delta function turns out to be equal to e to the minus as. Unlike the Laplace transform of the unit step function, there is no 1 over s in the denominator. That's because the delta function acts instantaneously. We're going to use Laplace transforms to solve an ordinary differential equation where the forcing function or input is a Dirac delta function. The equation that we're going to be solving is y double prime plus y is equal to delta of t minus 1. The forcing function delta of t minus 1 acts instantaneously at t is equal to 1. Let's begin by taking the Laplace transform of every term in the equation. We have the Laplace transform of y double prime plus the Laplace transform of y is equal to the Laplace transform of delta of t minus 1. I've written the formulas for taking the Laplace transform of a derivative over here on the right, and this gives us s squared capital Y of s minus s little y of 0 minus little y prime of 0 plus the Laplace transform of y, which is capital Y of s. And then we need the Laplace transform of our delta function. I put that formula right here. It is e to the minus as. In our example, a is equal to 1, so we have e to the minus s. Let's now substitute in our initial conditions, y of 0, y prime of 0. If we look up here, we see that y of 0 is 0 and y prime of 0 is 0. That makes it nice. So we can combine our y of s's, and we have s squared plus 1, capital Y of s is equal to e to the minus s. This gives us capital Y of s is equal to e to the minus s, all divided by s squared plus 1. Our solution, little y of t, is the inverse Laplace transform of capital Y of s. So it's going to be the inverse Laplace transform of e to the minus s. And let's write this next one as 1 all divided by s squared plus 1. Writing it this way, we have our e to the minus as, and we can write this one as capital F of s. Over here on the right, I put down the formula that we're going to need. We have e to the minus as times capital F of s, and the inverse Laplace transform of that is f of t minus a times u of t minus a. We need to find f of t minus a, or in our case, a is equal to 1, so we need to find f of t minus 1. Let's first find f of t. We know that f of s is 1 over s squared plus 1. So using a Laplace transform table, we get that little f of t is equal to sine of t. So we know that f of t minus 1 is sine of t minus 1. Now we can put all of this together. I'm going to draw an arrow here. We have y of t is the inverse Laplace transform of e to the minus as times f of s. So this is equal to f of t minus a. I'm just going to write the formula first, times u of t minus a. And let's note again that our a is equal to 1. So f of t minus 1 is sine t minus 1. And then we have u of t minus 1. And there's our solution. Notice that because of our step function right here, our system is at rest until t is equal to 1. And then at that instant, the forcing function strikes and the spring begins oscillating sinusoidally and continues that oscillation forever. And that's it. You now know how to model discontinuous inputs using step and delta functions and know how to solve differential equations with these types of inputs. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.